Okay, this is lecture 13, and before starting our lecture 13, I have one announcement. So lecture 14, so scheduled in this Thursday, will be a quite short one due to my personal condition. So it will be just a 30 minutes long lecture. So that is my announcement for lecture 14. And the next week we have the week for midterm examination. However, as announced in our syllabus, there is no midterm examination. Also, you know that there is no final examination. Instead of that, instead of this final examination, we will have a term project. So you have to submit your term project to me, then I will post it to my YouTube channel. So as just like our live streaming, then based upon your submission, I will make the grade for all of you. Okay, so do you have any question on my announcement? So first, in the next lecture will be quite short, and we have no lectures in next week, and we have term project. Then let's go to our discussion on Poisson equation. So up to now we have solved many things, but now it is the time to consider the major equation, Poisson equation, and of course we have to consider continuity equation later. However, this is the first time to be exposed to the Poisson equation. So since you know the Laplace equation, I wanted to make a comparison between Laplace equation and Poisson equation. So this is the Laplace equation. So simply speaking, when you take the Laplacian operator on your solution variable, then it should vanish everywhere. This is nothing but the Laplace equation. When we say Poisson equation in this course, actually we wanted to have this form. Here we have gradient of our solution variable phi. After that, if we just take its divergence, then it becomes just a Laplacian operator. However, instead of that, in this form, we have a position dependent coefficient epsilon here. So therefore, if we have this thing, it is no longer like just Laplacian multiplied by our position dependent quantity epsilon. So simply speaking, it can be this guy can be represented as epsilon times Laplacian of phi, and we have of course an additional term like this. So gradient of our epsilon dot gradient of our phi. This additional term can happen when we have this leading coefficient in front of our gradient of phi. So therefore, simply speaking, we have a big difference between Laplace equation and Poisson equation in the sense used in this course. Of course, I have to emphasize that in rigorous sense, when we say Poisson equation, actually we have to have the forms like this. This is the original form, mathematically sound form, called as Poisson equation. So Poisson equation simply means that it's a Laplacian. The Laplacian of our solution variable equal to a position-dependent source function. This is the exact form of Poisson equation. However, unfortunately, in this computational microelectronics course, due to historic reason, this form, so which contains position-dependent coefficient, is typically called as Poisson equation. Of course, in rigorous sense, it's not correct, but please understand this is a common practice used in this field. Okay, so anyway, whether that is called as Poisson equation or generalized Poisson equation, whatever, the meaning is quite simple. We have to consider the position-dependent permittivity in our consideration. Why we have to consider this position-dependent permittivity in real application? So that is quite easy to understand. For example, let's think about this structure. Here we have thin silicon, and it is covered by an insulating layer and another insulating layer. And let's say that here we have certain ohmic contact, and ohmic contact, simply speaking, means that here we have a certain metal, and here we have also another metal, and here also we have certain metal, but not directly attached to our silicon channel, but separated by this insulating layer, and this is also insulating layer, and say there is a metal and another metal. If we have this kind of structure, and if we wanted to simulate the electrical property of this domain, so this blue box domain, then what we have to do is to consider both of these insulating layers and this silicon layer. In this case, they have different permittivity, relative permittivity. For example, silicon's relative permittivity is known to be 11.7. And of course, in the case of insulator, we can find many of them. But for example, if we consider silicon dioxide as a representative one, then its relative permittivity is known to be 3.9. So simply speaking, even in this simple structure we have to consider in the real application, we have position dependent permittivity in our structure. So that's the reason why we have to consider this position dependent permittivity here. Of course, if we go to this condition, when the permittivity is a constant, then of course this term can be pulled out in front of this divergence operator. Then we can have the original form of Poisson equation. Simply speaking, the Laplacian of our solution variable phi equal to a position dependent source function. So that is the original form of Poisson equation. However, please note that once again, when we say Poisson equation, we are explicitly saying about this one considering position dependent permittivity. And if we have no net charge inside it, in this region, then of course this right hand side comes to 0, and now we can recover our Laplace equation. So from the viewpoint of our Poisson equation, the Laplace equation can be regarded as a very simple and special form, like constant permittivity all over our simulation domain and no net charge inside the simulation domain, then we can recover the Laplace equation. So now you can see that we are now generalizing our previous discussion on the Laplace equation to more general Poisson equation. Then now we can consider two different differences. One is, yes, this treatment of position dependent coefficient, and another one is this source term. So in this section we will consider source-free Poisson equation. Here source-free means that, simply speaking, we don't consider any of net charge density law in the Poisson equation. So in this section we will assume that this is 0. Then only the difference is, previously we had to consider this, and now we have to consider epsilon this. This is source-free Poisson equation in this lecture, and only difference is related with this one. So how can you consider this difference? Yes, however, now you are all educated with the box method, so now you can easily understand. Although it is written as this more generalized form, but this vector can be also considered as a flux vector. So whether that vector is given by just gradient of phi, or it is given by gradient of phi multiplied by certain position dependent coefficient, doesn't matter in terms of our box method. Why? Because when we evaluate this box integration, always we have the boundary values of this flux. Whether that has this special form or other special form doesn't matter when we consider this box integration. So we can apply the box method even to this case, but without considering that generalized form, I will just consider this one-dimensional form. Okay, so 1D case, how can you consider this additional term? So following just philosophy of integration over short range from x sub I minus half to x sub I plus half, we can just integrate it over that range. So lower position to the upper position, and this global derivative can be eliminated. After that, the remaining thing is epsilon times d phi over dx. What is it? This is the flux term evaluated at upper part minus epsilon d phi over dx evaluated at lower position. So simply speaking, here you can see my result. Here you have the permittivity evaluated at upper position and permittivity evaluated at lower position, and also d phi over dx evaluated at upper position and that quantity evaluated at lower position. So this is quite simple, and here please note that we have the permittivity evaluated at where? Evaluated at not xi or not xi plus 1. No, we don't have to consider the permittivity evaluated at the node point. Instead of that, we have to consider the permittivity in between. Same holds for this condition. Why that is so important? So I want to give you once again the diagram. Oh, yes. So please have a look at this example we have considered. If we have to introduce a two-dimensional structure, then where will you place our grid points? If we have to introduce some grid points, then we will place the grid point here and here and here and here. Of course, this is the mandatory one because these points actually interface between silicon and insulator. And also here we have to introduce the insulator between silicon and insulator. Okay, so if we have a certain shape, yes, there is one shape and another shape. We wanted to introduce some points to represent their shapes. Then what we have to do is to introduce certain position here, certain position here. These points are mandatory. If we don't define these interface points, then can you recognize the difference or the boundary between them? So it's not. So we have to introduce some interface point. That introduce some difficulties. For example, let's say that this is your silicon, and let's say that this is your silicon dioxide. Then simple question is here. Please have a look at this intermediate or interface point. What is the epsilon for this point? This point is actually the border between silicon and silicon dioxide. Then what is the expected value for your epsilon? Let's say there is one country and another country, and this is the border between these two countries, and let's say that there is a certain point, interface point. Then what is the nationality of this point? It is very difficult to answer because if we consider this point, it's good, or this point, it is also good, well defined. However, at this interface itself, it is difficult to ask this question or answer this question. So once again, let's come back to our permittivity. If we have, for example, one-dimensional structure, and let's say that this is the structure and it is the border between silicon part and silicon dioxide part. And if we consider this point, what is the permittivity at this point? It is difficult to answer. However, fortunately, our scheme just says that we don't have to consider the permittivity at this point. Instead of that, we are asked to answer what is the permittivity at this point, or what is the permittivity at this point. Can you answer this question? Then in this case, you can simply say that, okay, this is silicon, so 11.7. Okay, this point is silicon dioxide, 3.9. That is quite easy. So this box method can avoid a difficult question, what is the value of a certain physical quantity at the interface node. That can be avoided by this box method. If you have any question, then please let me know. Then let's go to our 2D or 3D case. Now, instead of our one-dimensional one, now we wanted to expand it to more general cases. So maybe you remember that we have already covered in the previous lecture box method. So after the box method, now we have to have the flux evaluated at an edge connecting I and J point. There is an I point and J point, and there are several J values. Okay, there can be many different J values when an I is given. Then we can consider the flux and the flux, another flux, another flux. These fluxes are calculated. After that, also we must consider the surface area, and it's like this, this, and that, and also this, and say that. Yes, so we have to consider this is A sub ij. This is the area of which is vertical to or perpendicular to an edge connecting I and J, and that is multiplied here, and we must consider the flux between I and J. And when we had the flux given by just gradient of phi, we were sufficient to consider just one-dimensional approximation. Take the difference between the solution variable phi, phi evaluated J point and phi evaluated I point divided by the distance between these 2 points. And when you go to the Poisson equation, then now we have more generalized form like gradient of phi, however, multiplied with position dependent epsilon. Then how can you do that? It is quite simple. We can just introduce epsilon in front of this gradient of phi. So you can see that here we just introduce this position dependent phi. However, this epsilon should be defined on H quantity, or somehow not exactly H quantity, but well, anyway, in this case we can say that this can be regarded as H quantity. Important point is it is not a vertex quantity, not a vertex related quantity. So this is related with H between Ri and Rj. We can uniquely consider what is it in this case. Okay, so now actually we have to consider this source term, but for a while we will just consider it as 0. So right now we can just use this form, but generalization to the more general case with non-zero source term can be done quite easy, because we can just multiply the volume of our box center at R sub I, so it is quite easy to understand.
플러스가 마이너스 붙여야 될 것 같은데 일렉트릭
Oh yes, so if we consider, if we introduce the physical meaning, if this flux is really equal to the displacement vector, then of course we have to say this one. Yes, so if we define this way, displacement, then this is the real form. However, in this form, Then now we have minus rho equal to 0. Please have a look at, we have a positive sign, so we intentionally applied minus sign, minus, and call it as the flux vector F. So why do you do that? So it is just a mere consideration, or usually students are more get familiar with this kind of action or this kind of operation instead of having minus sign. So there is no preference between this original physically correct form or scaled inverted form shown here. So it's up to you. Important point is, don't make any mistakes in your sign. If you make any mistakes in your sign assignment, then that will give you very unphysical result. However, as much as you are consistent with your sign, then it is always okay. So simply speaking, I want to say, let's come back to our original form. If we consider the discretized form of this equation, the original equation, then if we have to make the integrated and discretized form of this original equation, then we have to say that this is minus, because this is minus here, and there is minus because our d vector is simply given by this form. Okay, so yes, so that was really the correct comment, but in this case we are using just on showing an equation with minus sign in every term in the Poisson equation. Okay, that was a good question. Any other question? So I think that's it for our Poisson equation. In the case of Poisson equation, the flux term is relatively simple. It is because just multiply the form of our gradient, and gradient is a linear operator, so it is not that bad to consider this discretized form. Okay. Then now let's go to our 1D example. So source-free Poisson equation, and please consider a capacitor with two layers. So two layers means that each layer is 2.5 nanometer thick. So 2.5 nanometer, and another one is also 2.5 nanometer, and x equal to 0 is located here, and here we have x equal to 2.5 nanometer, and finally we have x equal to 5 nanometer here. And here we have a relative permittivity of 11.7 for the first half. Then what is it? So if you remember correctly, simply means that this part is silicon. And second layer from 2.5 nanometer to 5 nanometer has a relative permittivity of 3.9. What is it? Simply speaking, it is silicon dioxide. And we have applied just 1 volt difference between them. Then please calculate the potential phi. Of course, you will find that actually this kind of approach should be done in a care. So 1 volt is applied across the capacitor. So from now on, I will just say that phi equal to 0 here, and phi equal to 1 volt here. After that, I will try to solve the Poisson equation inside this silicon and silicon dioxide case without any source. So it has many things to be discussed in this course. However, please accept this simplification. The first thing we have to improve later is the treatment of this phi. Yes, so here we have 1 volt difference across these 2 points here and there. Therefore, we just applied 1 volt difference between these 2 points. But actually, since the material for this point and material for that point are different, there is no guarantee that actually potential difference is equal to 1 volt. Okay, so this one is really questionable. However, we will just treat this 1 volt difference in the potential solution, potential variable phi. So later, of course, we will make a more generalized discussion. And another one is here we use the source-free Poisson equation. So usually in the case of silicon dioxide, which is regarded as a perfect insulator, it's okay. Inside it, it is assumed that there is no net charge. However, when we consider silicon, can we assume that there is no net charge inside it? In the case of silicon, actually we have 4 different contributors to the net charges. So what is it? For example, donor. It can contribute to positive charge. Acceptor atoms that can introduce negative charge. Also, electron. It can contribute negative charge. Also, hole. It can contribute positive charges. So there are 4 possible contributors to the net charge density, but right now we are assuming that their sum is 0 always inside this silicon layer. This is also not a correct description and we must generalize it. However, for this simplistic example, we just consider even in this silicon layer we have just perfectly vanishing low value, so that is quite much approximated problem. Okay, so now you understand this 1D example does not correctly represent the real silicon dioxide system. In order to consider this silicon dioxide system rigorously, we have to consider more effect. However, the concentration or the focus is laid on just the implementation of source-free Poisson equation, just to guide you to the way to implement it. So please accept this kind of crude approximations. Then now it is the solution of your problem. So say that from the applied boundary condition, here you have 0 volt and here you have 1 volt. Why it is 0 and why it is 1? Why it is not, for example, why it is not 1.0 and why it is not 2.0? Is it because we just say it should be 0 and it should be 1? So this is just simply originated from our boundary condition. So our boundary condition should be revisited later because it is not a correct correct value. But anyway, for while, just accept this form. The real point we have to understand here is the slope change in this part. Please note that everywhere in this system there is no net charge density. So if we have no net charge density and if epsilon is constant, then what is it? If we have these two conditions, it is reduced to the Laplace equation. And here you are now looking at the solution of a Laplace equation. Here and there we apply the same boundary condition 0 volt and 1 volt, and solution of this Laplace equation just state that there is a straight line connecting 0 and 1. Everywhere it has the constant coefficient or constant slope here. However, now you can see that when we consider Poisson equation, simply speaking, epsilon is position dependent, then now you have different slopes. And here you can see that there is certain ratio. And there is a certain ratio. And here you have a slope. For example, this value is corresponding to 0.25. So 0.25 between 2.5 nanometer. This is the slope for this first layer. And how about this second layer? In the second layer, the remaining 0.75 is changed within 2.5 nanometer. Then which one has a steeper slope? Everybody can understand. Here we say that the second layer has the steeper slope. And what is the ratio between their slopes? If this is 1 and this is just number 3. Are you with me? So in this silicon dioxide layer, we have 3 times steeper gradient over our potential. Why we have a specific number 3? This is because you know that our permittivity ratio between silicon and silicon dioxide layer is 3 to 1. That's the reason why we have 1 to 3 ratio for our slope. So please note that this is epsilon and this is d5 over dx. Therefore, their product are really well matched between two different layers. So are you with me? Since in the silicon layer we have a higher permittivity, so slope is more moderate, and since we have a lower permittivity in our silicon dioxide layer, that is compensated by higher, steeper change of our electrostatic potential phi. Okay. Please note this one. So now you have your homework. In this homework problem, you can try to solve a similar system with different permittivity. So the first layer thickness is the same, 2.5 nanometer thick, and its relative permittivity is now 3.9, not 11.7. And second layer has the relative permittivity of 7.4. What is it? So this is corresponding to silicon dioxide, as we have already seen. And what is this 7.4? This is a representative value for our silicon nitride layer. So now we have a capacitor which is obtained by sandwiching or accumulating our silicon dioxide layer and silicon nitride layer. So I hope that everybody can solve this problem without much difficulty. Of course, the graph will be differed, and you will find that since the permittivity ratio is 3.9 and 7.4, so roughly 1 to 2, so you will find that actually the ratio of your gradient would be also quite close to 2 to 1 ratio. Okay, so now you will have, if you solve it correctly, then you will have a steeper slope and later moderate slope for your one. So this is first part of your homework problem 1. However, it has an important question. From the numerical result, please calculate its area capacitance. So capacity means that farad per square centimeter or farad per square meter, whatever. So with the correct unit, then please try to calculate this one. How can you do that? So please study by yourself. So this is a real challenge. So I think that everybody in this lecture room can solve this problem quite easily. So because it is not that difficult, I have already disclosed how can you do that. So here you have to use this one-dimensional problem everywhere. So please use this kind of discretization method everywhere in your program, then you can immediately get the solution. My point is, please try to calculate the capacitance. Capacitance is simply given by Q, C, V. So in this case, the goal is if you wanted to calculate the C of your capacitor, then we have to understand the voltage difference between them. Oh, in this case we have just 1 volt. It's okay. Then the goal is you have to consider the charge accumulated at the top and bottom of your system. So simply speaking, now you have this structure which is 2.5 nanometer thick and 2.5 nanometer thick. You have applied 1 volt. So here you have positive volt right here. Then what will happen? You can expect that there will be positive charge accumulated in this positively charged part and negative charges accumulated in relatively low biased contact. Then you have to find out what is the areal density of your collected positive charge. So are you with me? Then if you can calculate the coulomb per square centimeter by some mean, then that will give you the farad per unit area multiplied by volt unit. So that is perfectly matched to your definition for capacitance. So please, if you cannot oh, here is, I have made a capacitance, okay. So anyway, if you don't understand this one, so please do your self-study to understand how can you calculate this Q value. So I have one hint to you. So how can you calculate Q? Simply speaking, please consider our original equation. Here we have a net charge density and this is a displacement vector. However, rho can be regarded as just when rho is integrated over a certain volume, then that can be give us the quantity corresponding to the charge. Okay, so in this case, please have a look at this one. Here we have the Coulomb per square centimeter. So what we have to do is just to make a one-dimensional integration of your net charge density, because you know what is it? This rho is the quantity in per volume charge, and if you make a line integration, then you will get some quantity like aerial charge density. Okay, so that is the homework problem 12. So please try to solve this problem. It's not that difficult. So once you understand this one,
그러니까 지금 가정 전화 그러니까 그 차지 프리를 안쪽에서는 차지 프리를 가정한 거잖아요.
yes, you're right.
차지 프리가 아니면
Of course. So you're right. So as he asked, up to now we have solved a source-free Poisson equation. However, the source-free condition has been applied only inside this simulation domain. What happens or what is existing beyond this point? So I mean that here we have insulating layers, and what is it? What is the physical realization of this part and this part? These are just metal. These are just metal. In this part, although we have no net charge inside this capacitive layer, however, for these two metallic parts, we have tons of freely moving charges, so we can have this positive charge and negative charge quite freely. So actually, that kind of the displacement vector or displacement is compensated by this collective positive charge and negative charge. That is the physical meaning of this one. So inside our capacitor, we have displacement vector that is compensated by our rho inside our metallic part. But you know that since we have quite a good metal, good perfect conductor, so actually this positive charge is only existing the border between this capacitive part, insulator part, and metallic part. So we can just perform the integration in a quite short range to consider this positive charge. So please, if you have any further question on this problem, then please send me an email, then I can try to answer your individual questions. So anyway, I hope that the numeric solution itself is not that difficult because you have already done the Laplace equation. But point is to understand physical meaning of this calculation. Okay? So now let's go to the more advanced topic like with charge. However, in order to make it life easy, First of all, let's consider fixed charge conditions. So what is the fixed charge? So as I told you before, in a semiconductor, we can consider four different contributions from our species inside the semiconductor. For example, here we have a hole. One hole can contribute positive Q to net charge density. And each electron can contribute minus Q to our net charge density. And also, when donor is ionized with positively, then we can have positive Q. And if ionized acceptor is existing, then it can contribute minus Q. However, in order to make the notation simple, in this case we just merge them. So positive Q times ND minus NA is here written as net positively charged dopant density. So simply speaking, if you have n-type reason, then your n dop will be positive. And if you go to your p-type region where you have only acceptors inside it, then your doping density will be negative. This convention is widely used, so although not universal, but it is really widely used. So please get familiar with this notation. So usually positive doping density means that is corresponding to n-type region, and negative doping density is regarded as p-type region. Of course, please note that actually there is no rigorous thing like negative density. So can you consider negative density? minus 10 to the 18 per cubic centimeter. Actually, such kind of thing doesn't exist. It means that simply we have only acceptors whose density is 10 to the 18 per cubic centimeter. However, for our notation, we just made the negative sign to say this is p-type. So that's the reason why we have something like minus 10 to the 18 per cubic centimeters. But please don't be fooled by this notation. Always density is regarded as a positive quantity. So anyway, so now we have four different contributors to our net charge density law. So therefore, it is very difficult to say that we have exactly zero value everywhere inside our device. Actually, it's not. So in this section, we wanted to introduce this one. Okay, here we have a hole, electrons, and dopants. And actually, please have a look at this line. Calculating hole density and electron density is the main goal of all kinds of TCAD device simulation. So calculating this quantity is not easy. Actually, it is our ultimate goal. Also, calculating this n, it is not easy. Also, we have to perform a lot of computational effort to calculate this n. However, net charge density, it is really easy to calculate it. Why? It is corresponding to the net charge density, which is given by the process simulation. Once you learn your process simulation, now you know the dopant density. Then it is just used in our calculation. So therefore, in this part, to solve Poisson equation with fixed charge, of course later we have to say that Poisson equation with a charge, it means that just Poisson equation. Then we have to consider both of electrons and holes in our consideration, but for while temporarily just to neglect hole density and electron density. Why? How can we justify it? Just for our easiness of our implementation. So it's not rigorous. There is no reason to neglect them. But for while, please understand this situation and let's try to evaluate this equation. So there is no hole, there is no electron, and only dopant is important. Then can you expect the realistic application of this kind of calculation? Where can you find a point where we have no electron and no hole?
Depletion.
Yes, if we have PN junction, then there occurs certain range within this part. We have no hole, no electron. This is called as depletion layer, and in this case, this kind of description is quite good. However, I have one caution. When we consider the entire system, for example, if we consider this entire system, then unfortunately, for this depletion reason, it is good to neglect hole and electron, but it is not that good neglect electron and hole in this neutral n-type region and neutral p-type region. So although his answer was quite good, but in the case of a p-n junction, it is not perfectly applicable to consider this system. So however, anyway, that was a really nice try, and we can find another example of which can be described with this depletion case. It's like this. Have you ever heard about something like SY, silicon on insulator? So this is a quite old one, even used in these days. So it's like this. Here we have an extremely thin silicon dioxide layer. How thin is it? This is actually gate oxide. So this is just a few nanometer thick. And there is a silicon layer whose thickness is around 10 nanometer or 20 nanometer or sometimes 40 nanometer, something like that. And here we have very thick, nearly thick silicon dioxide layer. After that, below it, here we have once again silicon. However, its thickness is like orders of 100 micrometer scale. So please note that this is just a few nanometer, and this is a few 10 nanometer, and this is also quite thick, relatively thick. However, this is super thick, like 100 micrometer scale. So this structure is called as SOI because this silicon is laid on this insulating layer. So silicon on insulator. That's the reason why this one is called as SOI. Depending on the thickness of this SOI, actually, so depending on the thickness of this silicon layer, sometimes, for example, if we have a very thin layer, then there is no hole, no electron. If we have thin layer, then in this case, it is really good to assume that we have this kind of Poisson equation applied to this SOI system. So simply speaking, if we have a SOI system, then it is good to apply this depleted Poisson equation. And can you find more relevant, more state-of-the-art application for this equation? Actually, also you can find one. One is that nowadays the cross section of our transistor is just looks like this. Here we have just 5 nanometer thick silicon layer, and that is covered by one insulating layer. So this is now insulator, gate insulator, and this is our silicon channel. And here we have certain long wire. So this wire is used to conduct our electrons and holes. In this case, once again, in its equilibrium case, what is the hole density and what is the electron density? And it is good to say in low gate bias condition, there is no electron at all, there is no hole at all. So no electron and no hole. So even in this case, we can apply this kind of depleted Poisson equation for this cross section. So depletion can occur somewhere in the relevant technologies. So now, actually everything is the same. Previously we had no source term. Now we have source term. So I think that this left hand side is exactly as same as before. So you know this is d phi over dx multiplied by epsilon. Also d phi over dx multiplied by epsilon. But that is balanced with this term. This term is important and newly introduced in this section, and that is nothing but our net charge density integrated over small distances. This is upper position and lower position, and their difference between just integration domain. Integration domain. So although this is 1D, it can be regarded as nothing but just this volume or control volume of our omega. And of course here we have a minus sign. Why we have a minus sign? Because our left hand side term is not exactly divergence of d vector, but we are now considering minus d vectors divergence. That's the reason why we have a minus sign in it. So simply speaking, if you can do homework problem 1, then you can also consider this second part, this equation, just adding more terms in your right hand side. Then it is quite easy to implement it. So now let's go to our double gate example. In this double gate example, we have 5 nanometer thick silicon substrate. So here we have 5 nanometer thick, and that is surrounded by 0.5 nanometer thick oxide layer, and here we have also 0.5 nanometer thick oxide layer. And of course, here we have silicon, so its permittivity is 11.7, and here we have 3.9 and 3.9. And compared with our previous example, now we have to consider net charge density. Here we have p-type substrate whose density is 10 to the 18 per cubic centimeter. So simply speaking, if we have NP, though, in terms of positively charged dopant density, we have negative 10 to the 18 per cubic centimeter. So please understand this notation. This is nothing but just counting in terms of positively charged dopant. That's the reason why we have a negative charge. But in reality, there is nothing like negative density. Density is always a positive quantity. So this is just a notation. And we have 10 to the 18 per cubic centimeter. So how can we solve this one? In this problem, in this example, we will just assume, okay, this part we have 0 volt, and here we have also 0 volt across it. Then when we say that 0 volt and 0 volt, what happens? Obviously we have the entire, over the entire simulation domain, we will have 0 volt. So are you with me? But it's not correct. I'm wrong. I mean that even though we have applied 0 volt for left contact and right contact, since we have net charge density inside our silicon layer, it can introduce certain charge inside our system. Please note that our Poisson equation itself simply states that if we have non-zero net charge density, then it can introduce electric field over our simulation domain. That is the physical meaning of this Poisson equation. Now, we have net charge density inside this domain. So, although we have applied 0 volt and 0 volt to left and right contact, but we can observe the electric field inside our simulation domain. So, if we go to the solution part, this is the solution. Although we have applied 0 and 0 in this oxide layer and oxide layer, this is silicon dioxide and silicon dioxide. Due to the existence of our net charge density 10 to the 18 per cubic centimeter, we have this parabolic behavior. Of course, please have a look at the discontinuity here. Discontinuity of its slope. I mean that in this part, you have steep graph here, and here you have much moderate change. And what will be the ratio between these two parts, two graphs? So again, that will be 3 to 1, because this is silicon dioxide and here we have a silicon. So in order to compensate the difference between their permittivity values, so we have to have also differences in d phi over dx. So this is not included as your homework number 12, because I think that we have only 2 days to perform this homework number 12. So for this today and tomorrow, please concentrate on this source-free personification. So reproduction of this double gate example will be given to you as a next problem, next homework problem. So for a while, just to concentrate on your source-free personification. Okay, do you have any question?
다른 질문인데, 그러니까 지금 n이랑 캐리어를 다 제로로 가정을 한 거잖아요. 근데 처음에는 이온수랑 캐리어 수랑 정확히 일치해서 이제 전화 증성했을 텐데, 그러면은 이 캐리어는 이 가정에서 캐리어를 어디로 사라지고?
Okay, so let me just state his question once again. So, of course, when we have the charge neutral case, for example, in this case, our hole density would be originally 10 to the per 18 per cubic centimeter, and also our doping density or accepted density would be 10 to the 8 per cubic centimeter. If we have a charge neutral condition, then this one contributes positively and this one contributes negatively, so they are compensated to each other. That is charge neutrality condition. However, he is now asking this question. Okay, here we have silicon, 5 nanometer thick silicon, and oxide. And here we have dopants, which does not move, and here we have the same amount of a hole which can move. In reality, in this approximation, we are now saying that although these dopants are staying, however, we say that this moving particle called as hole are all eliminated from our structure. Then what is the possible way to escape them? So from the viewpoint of our holes, how they can escape from our system? That was his question. So my answer is like this. Although we are solving this one-dimensional structure, the realistic structure is just a long line of silicon which is sandwiched by our oxide layer. And finally, it is terminated by another metal attached to this silicon layer. So this metal can provide hole and electron, or sometimes this metal can consume hole and electron. So in this case, our holes originally located in this its local position, all consumed by this metal part. That's the reason why there is no hole remaining and only immobile particle called dopants are there. That's the reason why we have.
이게 옥사이드를 뚫고.
No. Please note that this is a two-dimensional structure, X, for example, Y, and here we have another G direction. And in this G direction, at the end of this G directional structure, we have metal directly attached to the silicon. So that consumes electrons and holes. Okay, so let me just repeat my previous announcement at the starting of our lecture. So next lecture, lecture 14, will be quite short, just 30 minutes long due to my personal condition. And next week, we have no lectures and no midterm examination. So you are free, but instead of that, I will give you some homework problems, so relatively higher difficulties. So please do your homework problem. And finally, you have no final examination, as I already announced at the beginning of our semester. Instead of that, you have to do term project, and term project will be received and that will be distributed or posted in my YouTube channel, and based upon the performance of your term project, the final grade will be largely determined. Okay, that was the announcement made in our lecture start. Okay, do you have any question? No, then I want to wrap up today's lecture. Thank you.